Hi, everyone, and thanks for coming to my talk. My name is Nathan Kallus, and I'll be talking about treatment effect risk, bounds, and inference. To motivate my talk, let me start with a hypothetical. Suppose you're running some sort of online platform or some app, and you're making a change to it. For example, you're changing up the machine learning pipeline to make it, say, more cost and energy efficient. But that's also going to have an impact on the recommendation algorithms on your app or platform, and therefore it's going to have an impact on users' experience. So first, you do an A/B test to see what the effect would be. So you ran this A/B test and you see, oh, maybe actually there's a significantly positive effect on engagement. Maybe you can't really measure stuff on retention. It's such a weak signal, but it looks overall okay. It looks like maybe this is an okay change, and you consider maybe I should go ahead and make the change. But then you say, okay, wait, let me first dig a little deeper and maybe understand the heterogeneity of the effect, say by the stratification by country. So then you look at the average treatment effect within the US, users in the US, within users in the UK, et cetera. And then you say, okay, some are positive, some are less significant. Of course, there's a lot of countries, and you say, oh, look at that. Denmark is negative and significantly negative. But then you also realize, right, that there's a lot of countries. This could occur by chance. Also, maybe Denmark constitutes a very small percentage of your user base. So you don't know. Yeah, you don't know what to make of that, really. So you could think also, maybe I should dig even deeper. Maybe stratifying by country is not enough. I could keep stratifying. I could now look at stratification both by country and device type. I can then stratify by version of the operating system, version of the app, et cetera, et cetera, et cetera. I could keep stratifying, keep stratifying. And the question is, at what point do we stop, or what lessons do we learn from this? On the one hand, we may think there are just too many groups, right? So you can alleviate this issue of multiple testing by having an omnibus test, you say using ANOVA, for their existing subgroup with a negative AT, right? So you test the null hypothesis of no heterogeneity at all. And if there's some group with a different ATE, then you can test that. But do we even really want to detect any tiny variation in any one tiny little subgroup after we stratify so much? Because they will exist if we stratify enough, right? If I stratify by version of the app, version of the OS, location, more specifically, past user behavior, I will find something. On the other hand, you might also feel at the same time that there may not be enough groups because you only have the data you have. You don't have data maybe on some important sensitive characteristics like gender or race or income. And it's really important to understand whether there could be variation along such dimensions as well, but we don't observe them. And maybe we don't even want to observe them for reputational, privacy, operational reasons. So there's not even enough groups at the same time. So in this talk, I want to propose treatment effect risk as a sort of answer to both of these questions. So the treatment effect risk is going to be the following quantity. It's going to be equal to the smallest within group average effect among all groups comprising some proportion of the population, say 10%, 20%, etc. So we're looking for what is the effect on the worst affected, essentially, in order to understand what is the risk of this treatment? What is the risk to some considerably sized subpopulation? And we're going to tackle two questions in this talk. One is going to be identification. This treatment effect risk is generally not going to be identifiable. So instead, we're going to look for what are the tight bounds on it. Then we're going to talk about inference. How do we actually conduct inference on these bounds from data? So first, let's set up the problem. We're going to have a population of individuals where each individual is associated with some features X that are observed and some potential outcomes for each treatment which are not observed. Right? These are the outcomes that the user will experience if given treatment 0 or if given treatment 1. And we're going to interpret these outcomes as their individual utilities. Right? So we're going to say that a high outcome is good for the user. Right? They engage more with the system. They enjoy using the system or the app more. Then the individual treatment effect, or ITE, is going to be the difference between those potential outcomes, and it's going to represent exactly what is the difference in utility for that individual. So for example, if 0 represents a status quo and 1 a proposed change, then the ITE is literally what change in utility is this user going to experience, a positive change or a negative change. The average treatment effect is going to be the expectation of the ITE, or equivalently, by linearity expectation, the difference in the expectation of the potential outcome of treatment 1 and the potential outcome of treatment 0. So you can either think about this as the average individual change in utilities, or the change in social welfare, comparing the world where everybody received treatment 0 and the world where everybody receives treatment 1. Those two are the same thing. Now, the data we're going to see doesn't have these potential outcomes. Instead, we're going to see data that consists of user features, some observed treatment that the user was exposed to. Okay, so A is going to take values 0 or 1, and the outcome corresponding to this. And we're going to assume that these are NIID observations of some generic draw X, A, Y. Now, the treatment we observe, Y, we're going to assume that corresponds to the potential outcome of the observed treatment. We're also going to assume that the treatment is ignorable, also known as unconfounded. And that's going to be guaranteed by design for actually running an A/B test. But actually, all we're going to talk about is going to apply the same to an observational study, so long as we assume unconfoundedness, which is a common assumption in that setting. We're also going to assume overlap, which again is usually guaranteed by running an A/B test. Otherwise, it's an assumption in an observational study. Now, this data with these assumptions is going to immediately identify some quantities. One quantity it identifies is the conditional expectation of potential outcomes for each treatment given features. Right? This conditional expectation is going to be the same as the regression of the observed Y on the observed X and the observed A. So therefore, it identifies this counterfactual quantity involving potential outcomes because we can write it just using observed data. We call this mu(xa). And then we therefore also identify the average treatment effect, which is going to be the average of the conditional average treatment effect, which is just going to be the difference between these two mu's, mu(x1) and mu(x0). Okay? So that Kate is literally going to be our best prediction for the individual treatment effect given covariance X. Now, how do we define the treatment effect risk given this? Well, we're going to do that using something called the conditional value at risk. So the conditional value at risk is defined by this optimization problem. So we're looking at the supremum over all scalar beta of some expectation involving the random variable and beta. Okay, so this is a quantity that's defined for each level alpha between 0 and 1 and a random variable z. And what this represents is roughly the expectation below the alpha quantile. Okay, so we look at the left tail of the distribution of z, and we say, look at, say, the 10% quantile, and look at what is the average at and below this quantile. So the C-bar is a little bit more clever than that because sometimes there might be an atom at the alpha quantile. Right? So in order to make it be equal to the, say, 10% worst affected, we may have to split the atom at the alpha quantile if there's such an atom. So that's what this more complicated definition actually does. For example, if there's some percentage right at the 10% quantile, we only want some of them in order to get a group that is sized 10%. Okay? And then the treatment effect risk at level alpha is simply going to be the conditional value at risk at level alpha of the individual treatment effect. So in other words, it's going to be the average treatment effect on the 10% worst affected if alpha is equal to 10%, for example. Right? So it's really capturing how might a smaller subpopulation, but still significantly sized, still restricted to be 10%, how they might experience the treatment differently than the average, right? Even if the average on everybody might be positive or neutral, the average on the 10% worst affected or the 20% worst affected can still be negative. And then we might worry about the risk, or maybe it's not so negative. And then we're like, okay, this seems like a less risky treatment, right? So it's really giving us a closer look into this quantity, right? And when we think about testing things on this statistic, on the treatment effect risk, we can, for example, test things like, does there exist a 10% size subpopulation that has a negative average effect, or that has an effect that is very significantly less than the average treatment effect? Those are the type of hypotheses that we can test once we think about the treatment effect risk. However, it is generally not identifiable from data. First thing we're going to do is we're going to talk about bounds for it. First, an upper bound. So the first bound says that the treatment effect risk, that is the CVAR individual treatment effect, is going to be upper bounded by the CVAR at the same level of the conditional average treatment effect at X. So this kind of makes sense. I mean, we don't see ITE, and our best guess for ITE having observed features X is K of X, right? If we observed some features, maybe we can try and best predict ITE as much as possible. So this gives us an upper bound. And in fact, this bound is going to be tight because if we're given any Kate, there's always going to exist some distribution with this Kate and the above is equality, right? So if you give me the data and you tell me this is the Kate, it could always be a counterfactual world where this is the Kate that really is, and this is actually equal. Particularly when is this equal? This is going to be equal when X explains all heterogeneity. So X predicts the individual treatment effect perfectly, right? There's no residual variance. So this suggests that, we get an upper bound for any stratification we make, and we get a better and better bound the more fine the stratification is, right? Another concern is lower bounds, right? So upper bounds is maybe the most important thing to look at because it can provide for a clear evidence of disparity. For example, if the upper bound is negative, then the treatment effect is negative. If the upper bound is very far from the ATE, then the treatment effect risk is very far from the ATE. So it's really, this is perhaps the most important quantity to look at because it's evidence of disparity. But we may also worry about what we may have missed. What sort of disparities do we not detect because we haven't stratified enough? Really, we have to think about what heterogeneity have we missed by only looking at X? What latent heterogeneity remains? So that would be a lower bound on the treatment effect risk. Now, for this, we're actually going to need to assume something about how much heterogeneity we could have missed. So we can do it different ways. If we assume that there is sort of an absolute bound in the difference between what the real treatment effect is on the individual and our best prediction of it, right? So we bounded by B, then we get one lower bound. And this bound is also tied in the same sense as before, right? But now with this constraint. Alternatively, we may look at what is the residual variance in the individual treatment effect after controlling for X, right? And we say maybe that's bounded. This is useful because this is actually much easier to calibrate to data, and you can actually bound that using just observational data. So if you assume this sort of bound on the residual heterogeneity, then you get another lower bound, and it's also tight. The next question is inference, because these bounds that I presented, they're going to capture the epistemic inerrant uncertainty if we're given infinity data, right? Even if you observe the exact distribution of the data of X, A, Y, the distribution that generated the data, this is the best you could do. This is the best bounds you can get. But it's only capturing this uncertainty given infinity data. There's also uncertainty given from sampling because we don't have infinity data. We have the n data points that we have, right? So how do we actually learn these bounds from data? So what we don't want to do is we don't just want to estimate Kate and plug it into CVAR. We don't want to just estimate Kate and compute it CVAR. We don't even want to do that with cross-fault estimation. That's not going to be enough. We need some sort of orthogonality, because what's going to happen is Kate can be a quite complex function. And even just making tiny errors in it will propagate and will affect our final estimate, which is kind of annoying because we might want to use some of the recent advances in causal machine learning to learn Kate, to use flexible models to learn this. But if we use flexible models, we will have slow convergence, we'll have some biases, and all of these will propagate to our estimate, and we'll be able to do inference. So in the paper, what I do is I develop a robust algorithm for inference. And unfortunately, I don't have time to go too much into it, but a couple punchlines of the results that this algorithm and the theoretical guarantees give us is that even if we learn Kate at very slow rates, something like just slightly faster than n to the -1/4, right, which is a non-parametric rate, means we can learn Kate with flexible models, right? If we just assume this rate, we're going to get fast convergence for the Kate CVAR, and we're also going to be able to construct value confidence intervals. So confidence intervals that are calibrated and whose coverage converges to 95%, say. Moreover, even if we incorrectly learn either the propensity or the outcome, right? And the propensity we never incorrectly learn in an A/B test, we know it exactly, so we always get that, then we still get consistency. So this is a sort of double robustness guarantee. Moreover, we get a even stronger guarantee than that, because even if we incorrectly learn the Kate, which is this kind of hard function to learn, we're still going to get a valid upper bound, right? So we might not get this best upper bound, but if we say, let's learn the best linear projection of Kate, that's going to capture most of the main effects, and it's going to give us some upper bound. So this is something called double validity. It's still valid no matter what. So these properties assure us that whatever we're going to do with these methods, it's going to be extremely robust, and we can really, really trust the results we get to really be bounds on the true treatment effects. Now, to actually demonstrate how this works in practice, I looked at a case study where I took data from an actual randomized experiment from this paper by Behagel, and I considered the following hypothetical that we could posit using this data. Suppose the French unemployment benefits, where they give some career counseling and they change the provider for this counseling from a private provider to a public provider. These are two arms that are present in this experiment. So we assume that private is sort of the status quo, and we're going to change to a public system. And then we're going to look at, well, how does this affect reemployment of these unemployed individuals with a 6-month window? So if we just take this randomized experiment, compute the ATE, we see a somewhat positive ATE. The confidence interval does contain 0, but it seems mostly neutral. In the paper, they actually, in Behagel, they actually do some IV analysis and tighten this more. Here I'm looking at the intent to treat analysis, where actually the ATE contains 0 in the confidence interval. So it looks like this is maybe positive or at worst neutral, so not too bad. Maybe a policymaker might look at this and say, okay, that seems like a viable policy change. It's not too bad. Maybe it's positive, and then maybe it involves some cost savings by moving to a public program. But the question we might ask is, well, okay, on average, it looks okay, but could there be a significantly sized subpopulation that has a clearly negative effect? Should we worry about that? Maybe by making this change, not everybody's going to be affected equally, and some will be harmed. We want to know what the risk of that is. That is exactly the treatment effect risk. So here, very quickly, the details are on the paper. So in summary, there were sort of two questions that our results help answer. Question number one is, what is the group treatment effect on the 10% worst affected group? Right? And can we bound that above by looking at the 10% worst affected group that's defined by X values? And can we bound it by low by thinking about what we could have missed? What are some residual heterogeneity that could exist? And we can then, using the inferential methods we developed, actually test hypotheses like, does there exist a 10% size subpopulation with a bad effect, right? Where bad could be a negative effect, or bad could be much worse than the ATE. So we gave some upper bounds that they were tight, we gave some lower bounds that they were tight, and we gave inference and estimation methods that are exceedingly robust and really assure us that whatever we report is really a legitimate bound, because it's so robust to learning things slowly or learning things incorrectly.